Hey everybody, welcome back to another chemistry video lesson. Today we're going to look at nuclear chemistry. We're going to go into the origins of what nuclear chemistry is all about. As you saw in that video at the beginning, a lot of people kind of conjure up that image of nuclear devastation and nuclear annihilation due to this word nuclear chemistry or nuclear reactions and stuff. They think of all the negative aspects of it. While that all is there, and we do think of that, there is a lot more going on than just bombs and explosions and radioactive wastelands and stuff. Makes for good science fiction, but it's also going to have a lot more at play in there. So in this video lesson, what I'm going to focus on is the origins of radioactivity. First of all, what radioactivity is, and then talk about where it comes from. And then I'm going to finish up with what nuclear equations are and how we represent these radioactive or these nuclear changes that are going on. So to start, we're going to focus our attention on the nucleus. Now, the nucleus is the center of the atom, and it's the protons and the neutrons that are in there. And we're going to use these as our, basically this is what causes nuclear reactions to happen, our protons and neutrons changing and transforming. So what happens is as a nucleus transforms, it's going to emit a particle, and it also emits energy. And that's what we call radiation, a type of particle and a form of energy that's going to come out of this nucleus. Now, keep in mind that this is a nuclear change. This is not a chemical reaction, so this is very different from what we're going to study for the rest of the year. So now we're going to focus just this chapter or just a section of this unit. We're going to focus on the nucleus. We're going to focus on protons and neutrons. For the rest of the year, we're going to be talking about electrons and how electrons transfer and jump around. Okay, so let's talk a little bit more about what radiation is and radioactivity and where all of this comes from. So the first thing we need to do is look at some scientific evidence. Oh, no, I take it back. Real quick, just want to make sure you guys review this if you have to, because we're going to use a lot of this isotopic notation. So isotope notation. Remember, this is the symbol, this is your atomic number, and this is your mass number here at the top. So review this because we're going to be looking at a lot of isotopes, because it's the isotopes that undergo the radioactive changes. So certain isotopes of certain elements are going to change into new isotopes. So protons are going to change and neutrons are going to change because we're changing from one isotope to another. So review, refresh your memory on isotopes and isotope notation. All right, now let's look at some data. All right, so what this is here is this data here showing us the ratio of neutrons to protons. So what scientists found is that we have certain numbers of neutrons that are in these atoms, right? So you got neutrons in there. And we also have some protons that are inside these atoms. So you got these protons and neutrons inside your nucleus, okay? And what they found is that the ratio of protons to neutrons leads to what's known as instability, meaning that the nucleus is unstable and it will change. So if something is unstable, like a table is unstable, it has the ability to fall apart and change. If a rock at the end of the hill is unstable, it's going to roll down, so it's possibly going to change. So when something is unstable, it means that it's possibly going to undergo some kind of change. So what would cause a nucleus to be unstable? Well, if we look at the data here, what this is showing us, these little dots here represent nuclei that tend to be stable. Now, out of the 2,000 nuclei that we know, about 279 of them are relatively stable. And I probably should put the term relatively in there because the term stability or stable here is kind of relative. So maybe a little quotes around it. Because even our most stable elements can still be unstable. Okay, but anyway, so these are the most stable nuclei that we have. That's what each of these dots along here represents. That's called the band of stability. If a nuclei has too many neutrons, then it will be unstable. So this area over here is your region of unstable nuclei. If you have too many protons, then you're going to be unstable as well. And if you have too many protons and too many neutrons, you're also unstable. So there's other dots here. There's another isotope here. There's another isotope here. Another one over here. Those would be unstable nuclei. Now these here tend to be those stable ones. So what happens is when this nuclei is unstable, it will go through what's called beta decay. We're going to talk about that later, but it will go through a change. So the nuclei will go through radiation and it will change to a new nucleus. So some of the protons will change and some of the neutrons will change. So that's what this stability is. Now notice how it curves up here. What this is just telling us is that it's not a one-to-one ratio. So it's not that every proton is neutralized or stabilized by an equal number of neutrons. As you get more and more protons, you get more and more unstable, meaning you need more and more neutrons to stabilize that heavier nucleus. And keep in mind that protons are positively charged. So when you have a lot of these positively charged particles in the nucleus, well, they're going to do a lot of interacting and repelling each other. Remember, the charge on a neutron is 0. So there's something going on here. We're not going to get into it right now. We'll actually add all this here. But just keep in mind that's where the origins of this come from. Okay, so now we know that nuclei are unstable and they change. So there's either too many neutrons, too many protons, or both too many protons and neutrons. Okay, so all elements 84 and above have this issue. There's just something about that many protons together just leads to very unstable nuclei. Okay, so that is your reason for instability. Here's some notation. So keep in mind, this is how we represent protons, neutrons, and electrons. That might be useful as we go through this unit and some other stuff in this unit. And let's take a look at the last section in this video lesson, which is on how we represent this. So let's say that we have copper 66. Okay, this would be an isotope of copper. So this particular isotope of copper is unstable. What it's going to do is it's going to break down and create zinc. Okay, so you get zinc 66. As a result of that, it shoots out an electron. So this is that particle that comes out, and of course also that comes out of here would be radiation or energy, and we'll talk about what that is in the next lesson or two later on. But for right now, this copper changes to zinc, it releases this particle here. What you want to know when we're dealing with nuclear equations is that the mass number and the atomic number must be equal on both sides. So we look at our mass number and our atomic number, and on both sides of the reaction, this is our change. This is what we had initially, and this is what we have after the change occurs. Okay, so copper changes to zinc, and it produces an electron. So afterwards, we would have an electron. Okay, anyway, so notice the 66 plus 0 gives me 66, 66. 30 minus 1 gives me 29 and 29. So therefore, we have a balanced nuclear reaction. Okay. Same thing down here. I think you can kind of figure it out. Now this is what's called an alpha particle. It's 2 protons and 2 neutrons. We'll get to that later. And it comes out and the lead turns into mercury. So therefore 200 plus 4 gives you 204. 80 plus 2, 82, and 82. Okay, so let's take a look at these two. Sometimes you're going to be asked to fill in the missing piece. So all you need to do here is just figure out the total number on this side. So here 14 plus 4, that's going to give me a total of 18. Okay, on this side I have to get the 18 as well, so therefore I'm going to have 17 on the top. So the mass number of this unknown element is 17. Down on the bottom I have 7 plus 2, which is going to give me 9, and I have to have 9 on the other side, so therefore this is going to be 8. So I know my atomic number is 8, so therefore you look it up on the periodic table, and I find that I have oxygen. Okay, same thing down here. I want to add these two add up, so therefore in this case 14 plus 18, I'm sorry, 14 plus 4 is going to give me 18. Okay, and I can easily figure out what this element is right away by looking at the periodic table. Element number 4 is going to give me beryllium. So beryllium is going to go in here. And for this missing piece, I know that the mass number has to be equal to 18. Now over here, what this number in front is telling me is that I have 6 of these neutrons. So I have 6 neutrons, each one with a mass number of 1. So therefore my mass number is 6, but I need a total of 18. So therefore over here, this must be 12. 12 plus 6 gives me 18. And the same thing on the bottom. Now the atomic number is 0, so that doesn't matter on this side. But over here I have a 6, so therefore this has to be a 6 as well. And again, if you look up on the periodic table, carbon is atomic number 6, so I can figure out my missing number. So all you got to remember is keep your mass number and your atomic numbers even on both sides. So there you go. There's your introduction to nuclear chemistry, why nuclei are unstable and why radioactivity occurs, and how we represent it with nuclear equations. Thanks a lot.